In section 3.5, we've learned a lot of new identity equations. The good news is that in this video, we're not going to learn any new information. We're simply going to practice applying the double angle and half angle identities. You may want to have those formulas nearby so you can refer to them as we work through these examples. Let's go ahead and get started with example 5. Find the exact value of all 6 trigonometric functions evaluated at alpha if cosine of 2 alpha equals 1/3 and 2 alpha is between 360 degrees and 450 degrees. Do notice that we're evaluating the 6 trig functions at alpha, but we are given cosine of 2 alpha. Now, if we know the location of 2 alpha, then from this inequality, we can divide all 3 parts by 2 and determine the location of alpha. Notice that alpha is between 180 degrees and 225 degrees. This means that alpha is in quadrant 3. This will be important to keep in mind to determine the signs of the 6 trigonometric function. Now, recall that there are 3 different double angle identities from cosine. I'm going to start with the one that is cosine of 2 alpha equals 2 cosine squared alpha minus 1. Then we'll be able to determine cosine of alpha from cosine of 2 alpha. The problem tells us that cosine of 2 alpha has a value of 1/3. So I'm going to plug that in. Notice I'm replacing the entire expression cosine of 2 alpha. I'm not plugging 1/3 in for the argument. And from here, we can solve for cosine of alpha. So if we add 1 to both sides, 1 plus 1/3 is 1 1/3 or 4/3. Then we can divide both sides by 2 or multiply by a half. 1/2 times 4/3 is 2/3. That gives us cosine squared of alpha. Then we can take the square root of both sides to solve for cosine of alpha. I'm going to go ahead and break that up into 2 separate radicals. And while I'm at it, I'm going to go ahead and be efficient and rationalize the denominator. So this gives us potential values for cosine of alpha. Now, because alpha is in quadrant 3, we know that cosine is negative in quadrant 3. So we can go ahead and make the conclusion that cosine is negative square root of 6 over 3. So there's one value of the 6 trigonometric functions. Now, we can certainly use identities to determine the values of the other 6 trig functions, but I think it'll be really efficient if we use a triangle. So I'm going to make a sketch here of the angle alpha somewhere in quadrant 3. We don't know the exact value, but we know it's between 180 and 225 degrees. So somewhere over here, we have the angle alpha. Now, we know that cosine of alpha is equal to negative square root of 6 over 3. Recall that cosine is defined as the x-coordinate divided by r. So we could say the horizontal segment here is negative square root of 6 and the hypotenuse is 3. We could then use Pythagorean theorem to determine the length of this vertical segment. So we could write this as negative square root of 6 squared. I'm just going to call that vertical segment b. B squared equals 3 squared. So we can solve this for b. My b's and 6's look alike. Read that carefully. Subtracting 6 from both sides, b squared is 3. Therefore, b is plus or minus square root of 3. But in this case, we're going to choose negative square root of 3 because it represents a negative y value. Now, from this diagram, we can determine sine of alpha. Recall that sine of alpha is the y-coordinate divided by r, or in this case, the hypotenuse. So sine of alpha is negative square root of 3 over 3. Tangent of alpha is opposite over adjacent, or the y-coordinate divided by the x-coordinate. So the negatives are going to cancel, and we do need to rationalize the denominator. So we would end up with square root of 18. 3 times 6 gives me 18. Thinking of 18 as 9 times 2, the square root of 9 is 3, and 2 is not a perfect square, so it stays under the radical. And the denominator, square root of 6 times square root of 6 is 6. We can reduce that just a little further by a factor of 3, and we end up with a value of square root of 2 over 2 for tangent of alpha. Once we have those three trig functions, we can find our reciprocal functions. So let's work on secant of alpha. Secant, remember, is the reciprocal of cosine. So I'm going to flip the ratio for cosine over. -3 divided by square root of 6. You can put the negative in the top or the bottom. I just translated it to the top there. We'd end up with -3 square root of 6 over 6. And that reduces by 3 to give us negative square root of 6 over 2. Cosecant, recall, is the reciprocal of sine. So we're going to flip the ratio we found for sine over and rationalize that denominator. We end up with -3 square root of 3 over 3, or how about just negative square root of 3. And for our last function, cotangent of alpha, we're going to invert tangent. 2 divided by square root of 2. Hopefully you're starting to notice this pattern, kind of like on the cosecant. When you take an integer and you divide it by the square root of that number, you end up with the square root. So for example, -3 divided by the square root of 3 gives me negative square root of 3. So 2 divided by the square root of 2 here will also give us square root of 2. While we begin that problem with an identity, we were able to evaluate the other 6 trig functions using an efficient diagram and the relationships that we learned in Chapter 1. Let's try a similar question, example 6, this time using a half-angle identity. Find the exact value of the 6 trigonometric functions at alpha if sine of alpha over 2 is equal to -1/3. So this time we have a half angle in the sine function. And we know that alpha over 2 is between 7 pi over 4 and 2 pi. We can also use that inequality to figure out the boundary for alpha. Multiplying all 3 parts of that inequality by 2, we can see that 7 pi over 2 is less than alpha, less than 4 pi. Both of those angles are larger than our common unit circle values. But if we use the strategy of counting in multiples of pi over 2, we can easily locate those angles. 1 pi over 2 is here, 2 pi over 2, 3 pi over 2. 4 pi over 2 is here, or 2 pi. 5 pi over 2, 6 pi over 2, 7 pi over 2. So 7 pi over 2 to 4 pi gives us a location in quadrant 4. So alpha is going to be a quadrant 4 angle. Because we're given the value of sine of alpha over 2, it would be a convenient time to use our identity for sine of alpha over 2. Recall, this is equal to plus or minus square root of 1 minus cosine of alpha divided by 2, where the sine is chosen based on location of alpha over 2. We can replace sine of alpha over 2 with its value, -1/3. That was given information. And then we can use this equation to solve for cosine of alpha. First thing we need to do here is get rid of that radical by squaring both sides. This yields the equation 1/9 equals 1 minus cosine of alpha divided by 2. Multiplying both sides by 2, we end up with the equation 2/9 equals 1 minus cosine of alpha. I'm going to add cosine of alpha to both sides and subtract 2/9 from both sides. So 9/9 minus 2/9 gives me 7/9. So from sine of alpha over 2, we have discovered cosine of alpha equals 7/9. At this point, you can use any identity relationship between cosine and the other 5 trigonometric functions to determine their values. But once again, I'm going to choose an efficient diagram to quickly and easily find the values of the other trig functions. Now recall, we determined that alpha is somewhere in quadrant 4. So I'm going to sketch it down here. This is our angle alpha. Because we know that cosine of alpha is equal to 7 over 9, we could determine that the horizontal segment of the triangle in this diagram is 7 and the hypotenuse is 9. We can then use the Pythagorean theorem to figure out the vertical segment of that triangle. So I'm going to say the hypotenuse squared, 9 squared, is equal to 7 squared plus, I'm just going to call that vertical segment b squared. So we have 81 equals 49 plus b squared. We'll subtract 49 from both sides. 81 minus 49 gives us 32. And thinking of 32 as 16 times 2, the square root of 32 then would be 4 plus or minus 4 square root of 2. Since we're dealing with a vertical segment in quadrant 4, we're going to label that segment as negative 4 square root of 2. Now that the diagram is labeled, we can easily identify the values of the other 6 trig functions. Recall that sine is the y-coordinates divided by the hypotenuse, so we get sine of alpha equals negative 4 square root of 2 over 9. Tangent of alpha is the y-coordinate divided by the x-coordinate. That's going to give us negative 4 square root of 2 over 7. We're halfway there. We've got 3 more to determine. To find the other 3, I'm simply going to use reciprocal relationships. Secant of alpha is the reciprocal of cosine. Cosine is 7/9, so secant is going to be 9/7. Cosecant of alpha is the reciprocal of sine. Sine is negative 4 square root of 2 over 9, so I'm going to flip that over, 9 over negative 4 square root of 2, and let's do rationalize. Multiply the top and the bottom by square root of 2. I'm going to call that negative 9 square root of 2 over 4 times 2, or 8. And the last one we need to find is cotangent of alpha. So we're going to invert tangent of alpha to get 7 over 4 square root of 2. I'm going to transfer the negative to the top for convenience. Then we rationalize the denominator, and we end up with negative 7 square root of 2 over 8 for cotangent of alpha. All right, we are on our way. Now, in those 2 examples, we are starting with an identity, and the first one was a double angle identity, the second one was a half angle identity, but then we resorted back to the basic definitions of the 6 trigonometric functions and a graph of the angle in standard position to determine the values of the other trig functions. That makes it pretty quick and efficient to work that problem. Let's try example 7. Find the exact value of sine of 2x given that tangent of x equals negative 8/15 and x is in quadrant 4. So we're looking for sine of 2x and we know tangent of x. Recall that sine of 2x can be written as 2 times sine of x times cosine of x. So in order to evaluate sine of 2x, I need to evaluate sine of x and cosine of x. I can obtain that information from this information. Because x is an angle in quadrant 4, I can visualize its location on a graph by sketching a random angle here somewhere in quadrant 4. So this is my angle x. Now, tangent is defined as negative 8/15. If you recall, tangent is the y-coordinate divided by the x-coordinate, so we can label the sides of that right triangle. We can then use Pythagorean theorem to figure out the hypotenuse of this right triangle. So we can set this up as horizontal segment squared plus vertical segment squared equals hypotenuse. I'll just call the hypotenuse c squared. 15 squared is 225. Negative 8 squared is 64. And when we add those together, we end up with 289, which happens to be, luckily, a perfect square. The square root of 289 is plus or minus 17. And of course, we'll use the positive value for the hypotenuse. From this triangle, we could observe that sine of x is equal to the y-coordinate divided by the hypotenuse, and cosine of x is equal to the x-coordinate divided by the hypotenuse. With those values in mind, we can come back over here and fill in more specific information. Sine of x is negative 8/17, and cosine of x is 15/17. I'm just going to use my calculator to find the product of those fractions at this point. 2 times negative 8/17 times 15/17, and I'm going to let the calculator reduce it as well. We end up with negative 240 over 289. That is the exact value of sine of 2x given the value of tangent of x. To work a problem such as that, it's very important to know not only your identities, but the relationships between all 6 trigonometric functions. Let's try one that's challenging as geometry problems were challenging. Example 8, it says, in the figure, angle B is a right angle, and the line segment AD bisects angle A. So in the diagram, we can see that both of these angles are defined as alpha over 2. Therefore, the entire angle here would be defined as alpha. If AB equals 5 and BC equals 3, find the exact value of BD. So we are looking for the length of this segment right here. This type of problem is really going to test our trigonometry skills. Because we're attempting to find the value of segment BD, I'm going to label that length x. Then triangle ADB is a right triangle. So we could make the observation using SOHCAHTOA that tangent of the angle alpha over 2 is equal to opposite over adjacent 5. Spotting the angle alpha over 2 also reminds us that we have 3 half-angle identities for tangent. I'm going to choose one of the half-angle identities without the radical to use for this problem. This is equal to sine of alpha over 1 plus cosine of alpha. Now recall, we just determined that sine of alpha over 2 could be expressed as x, that's the length of segment BD, over 5, and then we'll be able to observe sine of alpha because this angle here is alpha. So to obtain sine of alpha and cosine of alpha, I'm looking at the bigger right triangle. Sine is so opposite over hypotenuse. The opposite side is 3, but we need to calculate that hypotenuse. So the hypotenuse of the big blue triangle is going to be evaluated using Pythagorean theorem. 5 squared plus 3 squared equals c squared. That's 25 plus 9 equals c squared. 25 plus 9 is 34. That's not a perfect square, and we can't reduce it. So it looks like the segment of the hypotenuse is square root of 34. So sine of alpha is opposite 3 over hypotenuse square root of 34. Then cosine is adjacent side, that's 5 over the square root of 34. Now before I go any further, I want to simplify this complex fraction by multiplying the top and the bottom by that denominator square root of 34. So in the top, it's going to cancel the denominator, and in the bottom, we're going to be careful to distribute. Our equation becomes x over 5 equals 3 over square root of 34 plus 5. After distributing that square root of 34 in the denominator, you can see we still have a square root in the denominator. Let's go ahead and rationalize that at this point by multiplying the top and the bottom by the conjugate of the denominator. We'll obtain the equation x over 5 equals 3 times the square root of 34 minus 5. Foiling the denominator, we have the product of the first two terms gives us 34. Outside and inside terms cancel, and the last have a product of negative 25. Simplifying, we have x over 5 equals 3 times the square root of 34 minus 5 divided by 9. Notice I did not multiply out the numerator for this very purpose right here. We can reduce when we leave it in factored form. The last thing that we need to do to solve for x is multiply both sides by 5, and then we'll have x, the length of segment BD that we were looking for. We can express it as 5 times the square root of 34 minus 5 divided by 3. So we have analytically determined the length of that segment, analytically meaning we didn't measure it, and we have found it exactly. That's important for many calculations. You don't want to approximate. A series of approximations always leads to error, so being able to calculate something like this exactly is very beneficial. Let's try another one that is equally as challenging. In example 9, we have another right triangle. Angle B is a right angle, and the segment AD bisects angle A. So once again, this angle is divided up into alpha over 2 for both angles, so we'll call the entire angle angle alpha. If AB equals 10 and BD equals 2, find the exact value of CD. So this time we have the shorter segment, and we are looking for the length of the longer segment. Now, for ease of notation, we'll call the length of segment CD X. Let's make some observations about this diagram. First of all, I notice, looking at this angle alpha over 2, we know the opposite and the adjacent side. So we could observe from the triangle using SOHCAHTOA, tangent of alpha over 2 is equal to 2 over 10. And of course, we could reduce that to 1/5. I'll take one more line and reduce that to simplest terms. So tangent of alpha over 2 equals 1/5. We could also make the observation that tangent of alpha, that is the entire angle here, which is dependent on the larger right triangle, is equal to the opposite side, x plus 2, over adjacent side, 10. So here we have an expression for tangent of alpha over 2 and tangent of alpha. So we need an identity that expresses the relationship between tangent of alpha over 2 and tangent of alpha. Now, if you're thinking about your half-angle identities for tangent, none of those identities determines tangent of alpha over 2 in terms of tangent of alpha. However, we do have a double-angled identity for tangent, which looks something like this. Tangent of 2 alpha is equal to 2 tangent of alpha divided by 1 minus tangent squared of alpha. That, of course, is our double angle identity for tangent. But look at the relationship between the arguments on either side of that equation. This angle is twice as big as these angles over here. Or if we change our perspective, we could say that alpha is half of this angle right here. So we can also express this identity as tangent of alpha equals 2 times tangent of alpha over 2 over 1 minus tangent squared of alpha over 2. The relationship between the angles on the right and left side of both identities remains the same. So let's go ahead and evaluate tangent of alpha using this new identity. So on the right side here, we have 2 times tangent of alpha over 2. Recall, tangent of alpha over 2 is 1/5. So on the top, we have 2 times 1/5. In the bottom, we have 1 minus tangent squared of alpha over 2. That's going to be 1/5 squared. So simplifying, we have 2/5 divided by 1 minus 1 over 25. If you want to at this point, you can get a common denominator on the bottom and combine fractions. I'm just going to multiply the top and the bottom by 25. Either way you go will be fine. So on the top, we have 2/5 times 25. Notice 5 goes into 25 5 times, and that leaves behind 10 in the numerator. When we distribute in the denominator, we're going to have 25 minus 1, or 24. So at this point, we know tangent of alpha after reducing by a factor of 2 is 5 over 12. Now that's helpful information, but recall, we were looking for the distance of segment CD, x. So let's go back up to this relationship that we observed. Tangent of alpha, that's what we have right here, is x plus 2 over 10. So I can replace tangent of alpha with x plus 2 over 10, and I'll be able to solve this equation for x. When we solve for x, we'll have the length of segment CD. So I'm going to go ahead and cross multiply. We have 12 times x plus 2 equals 10 times 5, or 50. I'm just going to distribute my 12 12x plus 24 equals 50. Subtracting 24 from both sides, we get 12x equals 26, and we'll divide both sides by 12. 26 divided by 12, or when we reduce, 13 over 6. So we have found the length of segment CD with quite a bit of effort there. So as you can see, we didn't learn any new formulas in this particular video. We were just practicing using the identities that we've discovered in the context of these new problems. These are not easy by any means, and it takes a while sometimes to get started, but keep practicing, you'll get there eventually.